someone is requesting, but yeah. Uh, yeah.
Professor,
Yeah,
I I think your class is not recording, or you just started.
it's recording.
You sure? Okay, now it's starting. Okay, all right.
No, it was recording. But anyway. And yeah. Um yeah. And so yeah, coming back to the point, like if you have a lot of data points, how you calculate linear regression, and coming back to the same assumption you made when you start uh, applying linear regression to your data points, is that you assume that there exists a linear relation between x and versus the y. So there exists some kind of linear relation, either positive or negative, but in real case it might not be the scenario. So that's the first step of any algorithm in data mining or machine learning, is that which algorithm to apply at which point. As you have like a bunch of boxes, a box with like lot of algorithms, but you should able to apply only one algorithm which performs best, or a couple of them, but you should be able to figure it out which one does good for you. So now we are doing an experiment or example giving when to apply linear regression algorithm or when not to apply linear regression algorithm, based on some basic statistics measures which are available to us. I think everybody should able to mute themselves. Please mute all. Yeah. And yeah, and this is a small example where I mentioned that you imagine that blue line is nothing but uh, imagine the red line is nothing but a true line from which the data points are produced. So what usually people do is that they first take the equation of a line y equal to 2 plus 3x. For our simplicity example purpose, they won't do this in real time scenario. So you take this line 2 plus 3x and you take all the points from it and you add some kind of noise to it. Okay. And then you generate a large population of data points for this given line, and then imagine, as I mentioned before, you get a sample. You sample from a big population, but as you have like n number like 10,000 points, but you can only sample like 6,000 points. So every student in your class might sample 6,000 points differently, so they end up having different kinds of linear regression lines as shown in the right side. You can see all the blue lines are nothing but a different kinds of regression lines which students get when they sample different kind of points. So how do you know which line is the best line based on the sample of the population? Okay, so as I said that everybody in the class might get like different lines because you guys sampled different points from a given population. So we will be answering that question at the end of the lecture. So, and before that, I will be explaining some of the basic differences regarding to the nomenclature when applying population versus sample. Okay. So whenever you heard a name called parameter, they are referring to population. Even in our homeworks, when we are referring to parameter, we are referring to population. And we are when we are referring to something as a statistic, we are referring to a sample. So sample is nothing but a statistic of the population of the parameter. And whenever you see capital mu symbol, it does indicate it they are speaking about a population mean. And whenever you see small x bar or x cap, you are referring to a mean of a sample. Okay. And similarly with respect to the variance, whenever you see a sigma square with nothing indication bar and anything in addition to that, you are referring to a population variance. And similarly small capital S refers to a sample. Okay, same with the sigma standard deviation, which is nothing but a square root of a variance. So you can see this is how you calculate a population standard deviation on the first case, where the x is nothing but a every data point which you have, and mu is nothing but a mean of the whole population, and n is nothing but total number of data points which you have on the whole data population. And the second case, where you are calculating sample variance, sorry, sample standard deviation, everything would be the same. The you can see the small differences where the capital X actually got changed to small x, which does indicate you are referring to a sample. And the second thing is that capital mu is for the population mean, but in the next case you are basically referring to small x bar, which is like a mean of a sample, and the denominator is nothing but n minus 1. In case of a sample with respect to the population, it would be n. Okay, so n minus indicates that we are estimating one parameter in a population. Okay, that is the reason we do have a n minus 1 denominator in the sample standard deviation with compared to the actual population standard deviation. Okay, so what is meant by a standard error? Okay, now everybody knows that standard deviation is nothing but a formula. You basically take a difference between every data point with respect to its mean, and you divide it by either by n for population or n minus 1 for a given sample. So what does a standard error mean? So I want to explain by with a simple example. Like, imagine that a highway paving company is specialized in residential road surfing. You guys can read yourself. So, yeah. So, many of his clients seek out its specialized product, low noise payment, and recycled rubber can be added to asphalt mixtures to reduce the road noise, which appeals to environmentally conscious client. So, what they're saying is that you can basically add some kind of asphalt mixture to the road existing material to reduce the road noise. Okay, however, that if you are mixing few substances, the viscosity must be maintained within very tight limits, otherwise it might be too thick or too watery. Okay, the goal is the viscosity of a 3200. Means whenever you prepare buy any product, imagine you are buying a tin of a jar of some highway standard some material of this mixture. You should find the viscosity of 3200, otherwise your product is very bad. Okay, over several years of production and quality measurements, the company actually determined the viscosity of the population mean and standard deviation of the product which they are selling is having a mean of a 3200 and having a standard deviation, or I think it's a standard deviation or variation. Okay, having a standard deviation of 150. Okay, so you can see both they are referring to sigma and mu, which is nothing for a population. They are not speaking about the sample, they are speaking about the population mean and population standard deviation. Okay, so you can ask one important point. Okay, if you already know about the population mean and standard deviation, why are we even calculating rest of the parameters? But here we just mentioned it for our example, but in general or in a real time scenario that won't be the case. Okay, so what people does is that during the manufacture of each batch of asphalt, the quality control specialist takes 15 samples of material and tests the viscosity. So obviously they cannot test uh, each and every product which they manufacture, because they will be manufacturing maybe in a batch they can manufacture like 1000 to 10,000 tins, but they cannot test each and everything. So what they does is that they practically take on a random wise, they take 15 samples and they try to test the viscosity of that one. So you can see the in the points to note I basically mentioned that there is no way to test every ounce of asphalt. Okay, therefore company must take sample from a given big population. From those samples, HW must be taken to make inferences about the entire batch. Okay, and finally it's the same thing, like if you want to calculate height of a average height of a person in Georgia, you cannot go to every person to measure the height. You basically take a random population to do that. And I remember when I asked about the examples, like what kind of events people might plan to do in the spring, then you basically said that some people want to ask different departments, some people want to ask at students in the east, and other thing is the same thing. You cannot measure for all, so you basically take a 15 samples from a whole population, okay, or batch. Here the inferences made using the sample are by definition incomplete, therefore sample characteristics will always have some error built in. So this is one thing which we discussed previously, that there will be always a irreducible error present in your algorithm, because as you are not calculating for the whole population, there might be some errors inherently present in the statistics measures which are actually calculating. So you can see some people took 9 samples, and average sample mean or viscosity for each sample is given on the right side. As you can see, minimum viscosity is how much, 3200, and the variance estimate allowed is only 150. If you find anything after that, then your product is basically useless, so you should stop the production. So, okay. So you can see every sample, there is a bell curve. So everybody can learn it's called as a bell curve or a uniform normal distribution, and each have its own properties. So you can see the first one have its own mean, second one have its own mean, and everything. Okay. So what does he mean is, yeah, yeah. So what people does is that now I want to, we call this as a sampling distribution, because you are trying to sample from a big population. So we basically divided the big range into a frequencies. Okay, somebody basically said that okay, let's do in a given ranges. So you can see ranges can be divided according to your own wish, but you should be always liberal to divide from the top to the bottom. Okay, so you can see the least values around uh, maybe 3049 or something, yeah, in the range. So you basically need to do that, and you can see that I got frequencies of each, like how many values are available in each one of them. Okay, so we call this as a sampling distribution, or a average of all the sample means is nothing but a sampling distribution mean. Okay, E of x bar, you know what is x bar, as we mentioned in the previous slides. X bar is nothing but a mean of a sample. Okay, so this is anything I know some of you guys might not be familiar, but it does exactly look like a bell shaped curve. So you can see previous slides. Okay, sorry. Yeah, so you can see this curve shape. So this basically looks like a bell shaped curve, and our once you draw it, it also represents a kind of a bell shaped curve. Okay. So what does people say is that the middle item, which is nothing but a sampling distribution, is the actual sampling mean. What people say is that if you take multiple samples, multiple random samples, I basically right now only took 9 or some examples. But if you basically take like multiple of such that samples, the sampling mean, which is like x bar in our case, will reach mu, which is a population sample. So it's pretty simple. Intuitively, what they are saying is that if you have 10,000 points as a population, and for 4,000 points, if you get a mean of 5, but the actual 10,000 points mean is like 7. What they say is that if you increase your 4,000 points to 6,000 points, your mean will increase to 5.5. If you take from 6,000 to 8,000, your mean will increase to 6.3. And if you take total 10,000 points, your mean will be exactly 7. What they say is that as you keep on taking more and more number of samples, your sample mean at some point will reach the population mean. So that is the point where you decide you need to stop your experiment. Okay. And I want to say mention one more example what people try to do in real time situation, because in most of the cases they don't even know what is the size of a population. Like people don't even know what is the size of population is 10,000 or 20,000. Okay, so imagine a case where the whole population is like 10,000 but people don't know. Okay, imagine everybody don't know about that number. So what happens in that case scenario is that imagine I take 4,000 points now. Okay, then I got a mean of like 5.5. Then I add 2,000 more points. Then my mean becomes 5.7. Okay, then I add one more 1,000 point. Okay, then my mean only becomes 5.78 or something. Okay, as you keep on adding some points, you can see there will be a decrease in the total percentage of change. Okay, so then what happens is that you can say that okay, now my percentage of change is pretty less, so I reached almost a population mean using my sampling mean. Okay, that's what usually people tend to do in a real life scenarios. Okay, the expected value of the sampling distribution x bar is at best going to the estimate of a mu, which is a population mean. We would have to take every conceivable sample from population to match population mean perfectly. So this comes back to a point where you can never estimate exactly. There will be always some hidden error present in your statistics, because only thing is that you are calculating for a sample, you're calculating for a whole population but using samples, so but you never has a population. And but if you do that, what is the point of sampling in the first case? Okay, that's why the reason we went for sampling, because we don't know either what is the total population, or we don't have enough resources to do for the whole population. Okay, so the best we are going to do is able to do is find an interval estimate for the whole population mean. Our interval estimate will be influenced by sampling size and degree of confidence we are satisfied with. So you can see in this case one more thing which does matter is a size of the sample. Okay, some people if they take very less sample size, then it might not be a good estimate. Okay, a good sample size is always plays important part in your uh, estimating your total population characteristics. So finally, uh, you can see mean standard error of a population uh, divided by a square root of total number of items present or data points present in a given population will be the standard error of a uh, or standard deviation of a given mean of that sample. So imagine in the given scenario we have 15 samples and we know our standard deviation of the whole population is 150. Okay, so if you divide 150 by root 15, that would be the standard deviation of a given sample. And you can see, you can imagine as you increase your sample size more and more, then you basically end up at reaching the standard deviation of the whole population. Okay, so it's a small example. As the sample size increases, the standard error automatically decreases, because as you're estimating more points into your sample, you're reaching the overall size of a population. Okay. So a larger sample size narrows the standard error, as we saw that whenever the n equal to 500, you can see the blue curve, which is not wide, it becomes shrink. Uh, eh, okay, so and the second one would be n equal to 135, which is basically you saw that sample size actually decreased, then the curve actually bulged, and n equal to 15 is the last one. So this curve indicates that whenever the sample size is very high, then the curve becomes very slim, or else it becomes wide. Okay. So measure of variability. So I have two classes. I'm teaching this. Maybe I might be teaching two classes in this fall. So imagine I have class 1 exam scores and class 2 exam scores. Okay. But imagine I'm teaching two different courses. Okay. Not the same course. As the syllabus is different, everything is the different. I have first mean score of 85 and the second one has a mean score of uh, 85. Okay, can I say so same mean in case one data is more spread out, in the second case it is not as that spread out. Okay, because you can see in the first case you have a range of 75 to 90, but in the second case you have a range of 79 to 91. So in the second case the data is very clustered. In the first case the data is very different or spread out. It's same like our imagine our curve. In one case our curve is very thin, in the other case our curve is very wide. Okay, same mean or average, does it tell the whole story? Means can I actually compare two classes because they do have same mean? That's my second first question. Okay, so anyway, let me finish that answer. So you cannot actually compare two classes if they have a same mean. Okay, so then comes a point. Okay, I what is the how I can compare, or what is a way in which I can say that this class does perform this much when compared to this class or not. Okay, and then comes a point called z value, z score and standard deviation. So measure of distance from mean without units in measurement. So it's pretty intuitive, or like you can know by this thing itself how far is any given data point from the mean. Like if you have 5 points, imagine you have 5 points and you have a mean like 80 in that case, and if you imagine your new point is like 85. 85 is how much distance away from the mean? 85 minus 80, which is like 5 points away from the mean. So z value, the question basically z value answers is that instead of saying that mean is this one, data point is this one, can we actually say that how far a point is away from its own mean? How many standard deviations away or below from the mean is the data point? Okay, like imagine I have a mean of 80 and a standard deviation of 5, and the new point is 85. So 85 minus 80 is how much? 5. So 5 is how many standard deviations away from the mean? Our standard deviation is, imagine our standard deviation is 2.5 and our distance is 5. Then what you need to say is that the data point is 2 standard deviations away from the mean. Okay, and then what it basically says is that the z value is 2 in that scenario. Okay, the standard deviation becomes ruler of that sorts of measuring unit. So basically then if you take two students from two different classes, then we basically say, oh, in this class, the average is 80 and the standard deviation is only 2.5. So the student is actually two standard deviations away from the mean, or his Z score is 2. But in the second scenario, you can actually say that the average is 80 and the standard deviation is 5. Then if the score is 85, then you should say that Z score is 1 because the student is one standard deviation away from the mean. So this is the same thing which constructs the feet, yards, and light measurement. Okay, so these are standardized measures. Okay, Z score ignore the measurement units, inches, hours, scores, etc., but it tries to measure in the case of a standard deviations. Example: 50 x 50 standard deviation of 5. A value of 55 would be having a Z score of 1 because it's 55 minus 50 divided by 5. Okay, that's what we are basically comparing, is that how far it is away from mean in respect of standard deviation. So if 55 minus 50, which is like 5, and what is the standard deviation is always anyway here 5 here, so it is z score is 1. And if 55 is 5 above the mean and 5, so the a score of 40 would be what? uh, 40 minus 50, which is 10, divided by 5, which is minus 2. So the z value would be minus 2 because it's 10 or 2 standard deviations below the mean. If it is below the mean, it's minus. If it is above the mean, it's plus. And you basically, it's very simple. You basically take the mean, you take the difference and divide it by the standard deviation. Okay, so the whole thing is the data point minus mean value divided by the standard deviation. That's for the sample. If you don't know the sample, then for the sample it becomes small x minus, yeah, the first one is for the sample, which is capital X minus capital X bar divided by the standard deviation of the sample, which is indicated by small thing. And if it is a population, it's sigma and the capital mu. So I'm going to give basic example about jet score. So you can see a score, and of the score indicates the exam marks of each person student, and the mean is the class mean. And what you need to do is mean difference minus the score, score minus the mean. Okay, so you can see in this case it's minus 10, in the second case minus 5, and the final case it's plus 5. Okay, the only thing which you need to do is that 0 divided by the standard deviation. So you can calculate the standard deviation using our original formula, which is root of x minus x bar divided by the n, which is total number of the observations. So you can see it, then it would be what the standard deviation would be 7.90. So then you basically divide this value by the standard deviation, okay, which is 7.9, and you can see this one. So when somebody asks, what you need to say is that the jet value of the score 95 is 1.27, means it does indicate it was 1.27 standard deviations away from the mean. So for any given point you can actually calculate like this one. So but you can see what I did in the below is that I draw x bar, then what I drew is that x bar, which is mean plus one standard deviation away, which is 85 plus 1 into 7.90, which becomes 92.9. So you can do same wise, and then you can indicate the top points on where each one of it lies. So this is how it would be at the end, how each data point is located in the thing. So this is how you compare two samples if both are from a different thing. So you understand where we are going with this one. If you have two samples from a big population, how you can compare those two samples. Okay. Now we will be discussing about two important things. One is covariance and the second one would be a correlation. Okay. One sec. Yeah. So these two methods indicate whether you need to apply linear regression or not, or should you apply linear regression or not, or based on these measures itself. Even before applying linear regression, you can basically tell how well your algorithm might perform on a certain confidence level. Okay, so you can see standard S&P and Dow Jones are nothing but a stock market indicators, which basically indicate what happens to the stock. Okay, based on like top 500 stocks, and Dow Jones is also top 500 stocks. So you can see in the first, like today or like past 12 days indications, the S&P is 0.039 and the Dow Jones is 0.024. Same with, you can see it's a XY plot. I just plotted XY. And you can see a clear indication whenever X increases, the Y is also increasing. It's 0.0, and you can see this one. X increases, the Y is also increasing. Okay. So it's kind of having a linear relationship. Okay. How would you describe the shape of the pattern of the data? So you can see I can mostly draw a straight line through those points. Even though it's kind of a sublinear, let's call it as a linear. Okay. They seem to follow a linear pattern. If S&P goes up, so do the Dow Jones. Okay, increases as well. This better be the case. Why? Means they basically trying to measure the exact same thing, the performance of the whole stock market. Okay, so if both of you guys are trying to measure the temperature of Atlanta, so if one is measuring in one units and other is measuring in other units, but the whole thing should go up, right? Like if I'm measuring in centigrades and you're measuring in Fahrenheit, if one increases, the other should also increase. Okay, so this is called covariance. Covariance is nothing but if one thing increases, other thing also increases. Okay, or if one thing having a linear relationship with the other thing. So we'll be having two important things with respect to the covariance. Okay, so covariance is one of the family of statistical measures used to analyze linear relation between two variables. How do two variables behave as a pair? Okay, this is the main starting assumption which we made while going forward with the linear regression, is that x and y does has a linear relationship. Like if x increases, something happens to y either positively or inversely or negatively, but some relationship which is a linear exists. So covariance only measures the direction. Okay, covariance doesn't measure any numbers. Covariance, we'll be seeing examples in the upcoming slides, so you just don't get confused, but I'm just explaining some of the properties of the covariance. Covariance only deals with the direction, okay, not the strength of the two variables. So it basically says how much S&P Jones is correlated with the Dow Jones, or how much square foot is correlated with the price, or how much bill amount is correlated with the tip amount. It doesn't, it only indicates the direction, it doesn't indicate the strength. So this is the covariance formula, a sample covariance or a covariance formula. Okay, so it basically does is the same thing which you guys did in the linear regression. It basically takes the mean of x values and y values. It basically takes the difference between each data point of x versus the minus the y x bar mean, and divide it, multiply it with the same with the y values, and then you sum it and divide it over by the n minus 1 for a sample and n for a population. You can see the, I don't want to go through the nomenclatures every time, but you can see the differences. Are you asking sample means or a population means is the question always. Okay, so if you are taking a sample one, go to the left side. If you are taking the population, go to the right side. And this is how you compute the covariance. So before going for a linear regression, you can compute the covariance between the variables, then you can decide whether you need to do the linear regression or not. Only direction, that's what I'm saying, not the strength. Okay, you will know why I'm actually stressing that thing multiple times in the upcoming slides. So let's do an example. Rising Hills or any manufacturing company wishes to study the relationship between number of workers and the number of tables produced in its plants. Okay, to do so, it obtained 10 samples, each 1 hour in length. Okay, from the production floor. X is the number of workers and Y is the total number of the tables produced. Okay, so you can see, we know intuitively it has a linear relationship. If you have more people, you will have a more tables produced. And you basically do the sample covariance formula which we mentioned, just substitute all the terms. Okay, and I don't want you guys to type, so anyway I'm gonna explain. So what happened, yeah, so what you guys expecting the covariance to should be is that it should be having a linear relationship, right? Because you can see intuitively it does make sense that you have more number of people, you can produce more number of tables. And I basically calculated the whole formulation just the way I said it, xy minus x bar, which is nothing but a mean, y minus y bar, summate both of them and divide both of them by either population or a sample mean. Okay, so we are taking a samples from a huge population, so n minus 1, which is like total 10 samples, so I divided by the 9. So the covariance of a given sample for this example is 106.93. Okay. Okay, so when somebody asks you what is the relationship between workers versus tables production, you should always say both of them does has a positive linear relationship. You should ignore the size of the number, just look at the sign. Okay, this both are positively correlated, thus does indicate both of them having a positive linear relationship. If both of them doesn't have any positive linear relationship, then the output would be negative. Okay, so you can see, if you do this kind of plots for all your data, whenever you have a same data with respect to itself, everything will have a good relationship. But you basically, this is what we do is that you calculate what is the relationship between x1 versus the rest of the variables. So in this case, you can see x1 does have a linear relationship with x2, but it doesn't have a good relationship with the x3 and x4. Same, you can see in all the data points, if you have four columns, only x1 and x2 does has a linear relationship. x3 and x4 doesn't have a linear relationship exist with respect to any other variables. Okay, so what does it indicate in your linear regression function? If you include all the variables or like all the columns, then your algorithm will perform bad, because in that all the columns, only two of them only was a regular fit for a linear regression. So if you apply linear regression just considering the first two columns, then your model will give like a better accuracy when compared to including all the rest of the columns. Okay, so what I basically did in that figure is that you basically did a covariance measure or using the formulation between one versus the other. Okay, and what this figure is that, this is nothing but a kind of a mirror matrix. I don't know what you call exact term, mirror matrix. So if you calculate this one, you don't need to calculate this one. Okay, same with this other scenarios. Okay, the off-diagonal entries in the matrix provide the covariance between each the pair, and the diagonal elements basically between the same pairs. So it basically nothing but a variance itself. Okay, so we'll be discussing about correlation in the other upcoming slides, but I just want to mention about what is a covariance in this one. So covariance provides the direction whether you have a positive relationship, negative relationship, or a zero relationship between two variables. If it is a zero relationship, you should not do linear regression itself. While correlation provides the direction and strength, covariance provides only the direction, whether it's a positive or negative, but the correlation actually provides you the direction and the strength. Covariance result has no upper or lower bound, and its size is dependent on the scale of the variables. Okay, so right now what you saw is 106.203 or something. If somebody gets like 2300 or something, it doesn't matter, both of them indicating the same thing, both are having positive sign. Okay, that's the only thing we need to look whenever you're doing a covariance. It doesn't have any upper or lower bounds, while the correlation is always between -1 and +1, and its scale is independent of the scale of the variable. So correlation does has a limits of -1 to +1, and we'll be seeing an example. And covariance is not standardized, where correlation is a standardized. Okay, so think like a z score. In z score, we basically divided every variable with like a standard deviation, but in the covariance we basically don't do that. Okay, these are some of the uh, outputs of a correlation, and if you look at this one, you basically can decide whether you should apply linear regression or not. So in the first case, everything is nearly +1, then you can basically apply correlation. If it is -1 also, you can apply, because it's a negatively related, you will get a linear regression line in an opposite direction. But if it is near 0, you can see this scenario where all the points are spread out. So even though you apply linear regression, you will not get good accuracy at the output. And these are some of the non-linear relationships. I know that we discussed about like polynomial or exponential line sine wave at the start of the class. Okay, I'm just gonna give the correlation formula, the one which we are speaking about it in the previous slides with comparison to the covariance. So correlation is nothing but the same thing. you basically calculate the covariance first, and you basically divide it with the standard deviation of x and versus the into the standard deviation of the y. So the formulation is pretty simple. You basically calculate the covariance and divide it by the product of the standard deviations of the both the x and the y. Okay, so the same example. Okay, workers versus the production tables. Okay, and basically in the previous thing we got a covariance of 106.93. Okay, and now you know that you have x values and you have y values, so you basically can calculate the standard deviation using square root of x minus x bar divided by n minus 1. So once you calculate the standard deviations with x as 6.48 and for the y as 16.69, and when you divide both of them and you add it, the r coefficient or a correlation coefficient which we call is 0.989, which does indicate it is very near to the 1. Okay, and so you can see in this case what does it indicate is that uh, come on, give me one sec. So it does indicate that your correlation value is nearly +1. So it does indicate it's both of them having really good linear relationship. So if you apply any linear regression to it, you will get really good accuracy. If the value is really near 0, you can basically say that even though you apply linear regression, it basically is, gets very less value. Okay, so it's like strong positive relationship. So it does say that both the strength and the direction, where the covariance only mentions you about the direction. It's the same thing. The summary is that covariance does provide both the direction and everything. Strength, if it is +1, a very good; -1, bad. If it is 0, -1 is also good. Sorry, if it is 0, it's bad. Okay, and covariance has no upper limit, whereas correlation does has a upper limit. Covariance is nothing but a standardized, where correlation is a standard. You can see that is the only difference is that we are dividing the covariance by product of the standard deviations of the x and y. Okay, I don't want to go through hypothesis testing in this class. I might teach that in the next class. So regarding that's it for today's class. If you guys have any questions, you can ask me. But for any homework questions or Python related questions, please ask your TA for that. And one more thing, I think one student or someone mentioned to me in email that in one class some recording is not there or something. But yeah, it's not compulsory for me to actually keep the recordings, because as I'm teaching the class as a synchronous mode, if I don't teach it as a synchronous mode, then then only it's compulsory for me to like keep the recording on. So if you miss the class and if I miss the recording, then it's not my fault. Okay, if I take it as a asynchronous class, then if I miss the recording, then it's my fault. So you should always attend the lecture whenever I'm teaching the synchronous way. So I'm actually planning to do asynchronous. Like I'm not sure. Maybe like not for the next class. I'm not sure. I'm gonna mention in the iCollege for like next 3 to 4 classes or something. Then I can send you a survey whether you like asynchronous or synchronous class. Then I might decide in future what I need to teach. I hope that's a good idea. But uh, it's kind. I read your question. It's kind of same. The formulation is kind of a same. So I can go through that actually. So you can see the standard deviation. You're basically taking square minus these things, but I think you do the same thing in the standard error too. I think both of them are different. So standard error is with respect to the standard deviation divided by the square root of n. So I think first you need to calculate the standard deviation to get the standard error. So it's like you calculate all the deviation, then you divide by the square root of total number of values. So even I get confused sometimes with this one. Yeah. I hope you understand that point. So if you have any other questions, you can ask me. I hope no questions anymore. Can you upload today's lecture? Yeah, I will be uploading it. Just give me a second. I hope you guys will be able. Yeah, I uploaded. If anybody has any other questions, you can ask now. I hope no more questions, but uh, yeah, thank you everyone. Then see you on like Monday. Will you post study guide for exam? No, I won't be posting any study guides also for the exam. Sorry about that. As preparing the slides does take a lot of time, and usually if you prepare all the assignments and in class slides well, you should be good enough for the exams. So that's how usually my exams are. Like my exams are pretty hard, so if you don't listen the class and try to attend, that would be pretty nightmare. And if you do the uh, assignments all by yourself, and if you read the slides and come to the exam, then you should be in a good position. Are there any previous sample exams so we can have a? Sorry, I don't have any sample exams on previously of questions, but I do can give you like what are the questions not what are the question, like how many questions of multiple choice I plan to ask, or how many questions of uh, theoretical questions, that kind of like subdivision I can basically say, not exactly of what happening I cannot say. I don't have any like previous samples of those things, because I gave if I give you previous samples I need to prepare a lot then. So yeah, I can actually subdivide and go through like what I will be giving in each sections. And I'm still not sure about like how people try to conduct the exam. I know that you might be taking different classes. Some people want to give it as an open book, but keep your video on. So we'll go to the example here. If we have a review time, I will definitely go over the problems. But as you can see, in most of the slides are pretty clear. So even in the review section, I basically go to that slide and say that, okay, this is what we did there. I might not take that much time in explaining but I'll try to go through if we have a time most of the examples, because the next class we will be learning a bit of clustering. Will the exam be on iCollege? Uh Victoria, I basically, you can call me dumb in that case. I basically don't know how to conduct exam at this point. Means previously it is in class, it used to be very easy for me, but now I'm not pretty sure. I basically have a mentor for me. Usually every professor has a mentor, so uh, my mentor might be helping me in like conducting on how I need to conduct the exam. Should I just turn your videos on so that I know basically what you're doing? I know that iCollege does has a feature of conducting exams where it can actually track your browser, but it's a paid version. So I'm always against people paying money. I don't like that concept of people buying textbooks or paying money for softwares and all. So once I figure it out on how I want to conduct in the best possible way, with you mostly not paying enough any money, I'll try to figure that way out. And if it is that's not the case, we will have to block of 5 hours that we have to take it within, or it would be in the class. It will be only in the class time, so you should not able to block any other time. So mostly it would be the exact class time only, and it would be exactly the uh, 1 hour 45 minutes exam. That's our class time, right? Yeah, it would be only the class time would be good enough for that one. And yeah, you can ask me if you have any other exam related questions, but don't ask me how I will conduct that one. I'm not sure. Once I figured that out, I will definitely let you guys know. And I hope no more questions. Then I'll stop my recording and I will end the meeting. Thank you, Victoria. You're welcome. Bye, everyone. Sorry for the delay. My laptop got messed up at the start, so that's the reason I came like 5 minutes delayed. Bye. Yeah. Stop.